In the first episode of a Blueprints 101 course over on our Patreon, I quickly showed a Houdini version of the Zellgrid project we built in this course. And today, this Houdini setup finally gets its own tutorial. First of all, the setup that we're going to build today is going to be a sort of bigger setup, and I want to build it in steps. And this is also what you're going to find in the scene file downloads. You're going to find these 4 steps, and these are the main steps that we're also going to take in this tutorial. And for the first step, the first little setup that we're going to build in here is this single grid inside of Houdini that just further and further subdivides based on a curve that we're drawing onto this grid like this. So let's first of all build this right here. Let's drop down a geonode, let's dive inside, and let's first of all bring in on-base objects. This will of course be a grid that I want to set to a size of 2 by 2, 3 rows and columns to get this 4 by 4 grid as a starting point. And then I also want to bring in a curve that I drew earlier, like this. And next I want to animate this curve, and I want to animate it using a carve node. And if I wire this in and not select first view but second view, I can now have this curve animate out in my scene. Now, the way I want to animate this is I want to first of all jump to frame 1. And I don't want to set this to 0 because in this case we don't get a curve at all. But I want to set it to a very small value, 0.01, because some parts of the setup that we're going to build shortly will require us to always have at least a short curve segment. So with this, let's set a keyframe as this small value, and then let's go to frame 48, drag this out to 1, and add our second keyframe in here, and now our curve is animating. Next, I want to initialize some attributes here on my main grid. And this is going to be a little bit odd because I'm going to put a lot of attributes that we usually associate with points inside of Houdini. I want to have them on primitive level in here. This is simply because in the end, the node that I want to use at the very end to get my effect in here is a subdivide node to further subdivide my grid. And the subdivide node just really likes prim groups and prim attributes, so it's just a bit easier to keep all those things first of all on primitive level. So for this, let's drop down a prim wrangle. Let's call it init attributes. And for now, for this first step, this is just going to be a single attribute, and this is going to be a p-scale attribute. Again, now on primitive level. Let's write f at p-scale, and in here I want to store the side length of all my quads in here. So the side length will be, in this case, with a 2 by 2 grid, a side length of 1. And again, if we are going to subdivide later, then this value will also get smaller and smaller and smaller. With this done, we can now drop down a solver because again, we want to do our subdivisions iteratively. So let's wire in both of our noodles in here. And let's jump into the solver. And first of all, in here, I want to find out if the curve that we're drawing in here, and let's maybe ghost this for now, if the curve that we're drawing in here is running through one of those quads. And if it is running through one of those quads, I want to set a group on this quad that is going to tell Houdini, hey, I want to subdivide this later. So to find this out, let's first of all drop down another primitive wrangle. Let's wire this inside here, and let's also take our animated curve and put it into the second input. I want to first of all get a vector that is pointing from the center of one cell to the closest point on the curve. Let's actually create this vector, and let's call it dis for distance. And to get this vector, I first of all want to find the closest point on my curve. And for this, I can use the min-pos function. And with this function, I want to search on geostream1. And I want to search from my current prim's center point, which is v at p in this case. So this is the closest point on that curve. And to actually get a vector that is pointing from the center to that closest point, all we have to do is do some vector subtraction and subtract our center point from this. So minus v at p. And now we get a vector pointing from the center to the closest point. So with this vector, now we can check if this curve is actually running through our primitive. And we could either just take the length of that vector, however, this would give us a sort of circle. However, to actually make sure that the line is really running through our primitive, what we actually want to do is we want to check the x and y component of that vector. So to do this, let's first of all write the check. So we first of all want to care about the x component of our distance. So let's write dist(x). And depending if our curve is here, on the left side or the right side of our square, this vector on this value might be positive or negative. So to get the absolute value, let's wrap it inside an absolute function. Let's write abs distx. And we want to check if this is smaller than half the size of a current cell. So add p-scale divided by 2, like this. And we want to check this both for x component and our z component. So let's copy this. Let's write an AND statement in between. And let's check on the z component. So this is our comparison right here. Let's also add with a semicolon. What we now want to do is we want to set a group depending on if this is true or false. And the easiest way to do this is to simply create a new attribute, call it I, add group underscore split, and set it equal to this expression. And now we actually set a group if this is true or this is false. To quickly check this, we can go to the binding step and we can, in the output selection group, write a split in here. And let's scrub through our timeline and see if this works. And yes, this seems to work. Now we're almost done with this wrangle right here. The last thing that we want to do is just a safety measure, because again, this is running in a solver. This is running over and over and over and over again. And if we're subdividing over and over and over again, our scene will get pretty heavy pretty quickly. So we want to limit this only until we reach a certain small p-scale value, and then we don't want to subdivide anymore. So to quickly do this, let's first of all write our if statement. So if f at p-scale is larger than some small value, so 0.04, let's say, only then won't we do this split check. So let's just paste it in here like this. And now this is our safety limit. So after we're done with this check, we can do our subdivide. So let's drop down a subdivide now. And of course, the only thing that we want to subdivide in here is our split group, like this. And also we want to set the algorithm not to a algorithm that does some sort of smoothing. So let's set it to bilinear. And this will keep all the faces in here nice and square. And then finally, for all of our split cells, we then also want to again make our p-scale attribute smaller, because we need this up here in this wrangle. So let's drop down another prim wrangle, and to keep this a bit more readable, let's also name this. Let's call it find intersection, and this one set split attributes. And again, this right here should only run over a split group, and all we want to do in here is half a p-scale. So f at p-scale, we want to multiply this by a value of 0.5, like this. And then also one last very important step. We also, for each run of our solver in here, we want to recalculate this split group, and we want to discard the old split group. So for this, let's drop down a group delete and finally get rid of our split group like this. So this should be everything we need to do in here. So let's give this a quick test. And yes, this is exactly what our setup does. So we got that first part done. Let's take a look at the second part. For our second part, what I want to do is I want to assign a couple of random shapes and a couple of random colors to each one of our cells in here. So let's do this next. So for this, let's first of all jump out of our solver and let's maybe tackle the shape first. What I want to do for my shape is for each one of my cells in here, I want to define an ID attribute. An ID attribute that I later want to use with a copy to points node to copy the right shape onto the right point in the end. I first of all again want to create this ID attribute, and let's call it I at OID for object ID. And in the end, I want to first of all choose this randomly. So let's pick one random number and let's just calculate this based on our prim number like this. Then in the end, I want to have 4 different shapes. So since this value is between 0 and 1, I can multiply this by 4, and I can also floor this value. So always round it down. And now this will give me random values between 0 and 3 for my 4 different shapes. And then finally, since I'm storing this in an integer attribute, I want to also convert it into an integer. So let's use an int function right here. So let's do a quick test. Let's take a look at the GeoSpreadsheet. Let's go to the primitive tab. And we should have values between 0 and 3 in here. And this is exactly what we're having. Now, of course, if I set this randomly in here, I also have to set this randomly for every new cell that I create in my solver. So let's copy this line of code right here. Let's jump into the solver. Let's go into the set split attributes wrangler in here. And let's just add this line in here as well. and this will only run over our split group, so every new cell that we're creating, and again, assign a new shape to it. Now, next we have a problem, because right now we're just dealing with primitives. However, in the end, I want to use a copy to point sub, so we need to convert our primitives into points next. And again, for this, I'm going to use, well, a primitive wrangle. Let's write this down. Let's call it prims to points. And what I want to do in here is quite simple. I first of all want to remove my current primitive that I'm running over. So let's write remove prim. And this should be on geostream 0, my current prim num. And also I want to remove every point connected to the primitive as well. And I can do this by writing a 1 at the end. And then for every primitive that I'm going to remove, I want to add 1 point. So int pt is equal to add point. And I want to add this at the midpoint of each primitive. And also on geostream 0, let's write 0 and v at p in here, like this. And then finally, I want to bring all my attributes that I have on my primitive level in here. I want to bring this to point level. And for this, I can use a bunch of setPoint attribute functions in here. So setPoint attrib, again on geostream 0. The first one that we're going to need is our pscale attribute. We want to write this onto the point that we created, so pt. The value should be the attribute coming from a primitive, so f at pscale. And the mode should be set to set, like this. And then let's do the same for my object ID. So let's copy this. And for now, we're done here. So now we have, instead of a bunch of primitives, we have a bunch of points. And on those points, we have our OID attribute and our pscale attribute. So finally, what we can do now is we can use our copy to point sub. And I'm going to bring in my base shapes. For this setup right here, I just quickly package those into a subnet. And all I'm doing in here inside that subnet is I'm bringing in all my different files for my different base shapes. And on every file node in here, I have to set this to load in as packed geometry and to display as full geometry. Again, we're copying this to a bunch of points, so let's be efficient here. And then the only other thing that I'm doing in here is I'm scaling them down to this value right here, because again, I imported them at the wrong scale. So to finally make this work with our copy to points in here, let's first of all wire in our geometry and our points. This is already sort of working. Now we have to get our object ID attribute to work in here as well. For this, first of all, the geometry coming from a subnet in here also needs an object ID attribute. For this, we can use an enumerate sub. And in here, let's set this to primitives. Let's call it OID, and this should be an integer. And then on our copy to points node, create a piece attribute and activate a piece attribute, and let's call it OID. And now this is working. And our animation is also working. Next, let's do the colors. And first of all, I want to, in the end, build the way I want to implement those colors. So for this, I want to drop down a color node. Or let's say I want to bring in a color node, because this takes a while to set up. So this is the end result, and this is, in my opinion, the easiest way in Houdini to create a sort of color palette. So what I did here is I set the color type to ramp from attribute. And the attribute that we want to use in here is called CID, and we're going to create this shortly. And then the ramp is just simply 5 different colors at these specific locations at 0, 0.2, 0.4, 0.6 and 0.8, and all of them have a constant interpolation. So we get these 5 different color bands, and this is our color ramp in here that we want to use in the end. So let's wire this in here, and now let's implement our random color attribute. So for this, again, we want to start out up here in initialize attributes, and we want to create a CID attribute. In this case, since in the end we're using a color ramp down here, this should be a float between 0 and 1. So f at CID should be again equal, first of all, to some random value based on a primnum. So let's write rand at primnum, and let's make sure that we use a different seed in here. So let's just multiply it by 1, 2, 3. Then I know that I have 5 different colors, so let's multiply it by 5. Then again, let's floor that value so that we just get values between 0 and 4. And then to finally get this to this between 0 and 1 range that we're after here, let's also divide it by our number of colors. So divided by 5.0. And now again, if you take a look at our geo spreadsheet in here, we should get the values between 0.0 and 0.8, which is what we need to grab all those colors inside a color ramp. Next, again, we need to set this attribute right here both on our initial cells and the cells that we're going to create next. So let's just copy it again. And again, let's jump into our solver and again, add this line to our split attributes as well. And then finally, we need to pipe this attribute to points as well. So let's go to a prems to points wrangle in here, copy this line of code. Let's grab CID and let's bring in f at CID like this. Let's see if that worked. We first of all have to reset our solver like this. And this seems to have worked. And now we also have differently colored cells. So this is currently working. Now, the next big step that we're going to implement in here, we want every cell to explode out from its center to its actual position. So how can we implement this? First of all, since we're dealing with animations and we're dealing with procedural animations, the first thing that we want to add in here in our initialize attributes is we want to implement some timing attribute. And I'm going to call it f at age. And let's first of all, again, initialize this to 0.0. And then in the end, we also want to save not only the current middle location of every cell, but also the middle location of the cell it came from, its origin position. So we can again push it from that position to its current position. So to do this, let's also create one attribute for this. Let's call it v at orig or origin. And let's for now again initialize it to v at p. By now you've guessed it, we have to initialize those attributes both right here at the beginning of our setup, but also in the solver. So let's just copy both of them right here and jump into the solver. And let's go into our set split attributes and paste them here. Now, this is going to work currently only for our age. For our origin, we need to look out here because at this point in our setup, we already passed the subdivide node. So we already subdivided our cell. So we've lost our original position. So what we actually have to do for the origin in here is we have to get another set attributes wrangle in here and put that before the subdivide. Save it in here. So to quickly do this, let's just create a copy of this. While this up here. And for the upper one, we want to get rid of everything but the v at origin line, like this. And down here, we just want to get rid of the v at origin line. So in here, we're setting the origin point. In here, we're setting the age and everything else. And then what we also need to do in here, since we have that age attribute, we have to increase it for each loop's iteration. So for this, after our group delete, let's bring in another primitive wrangle. This will run over every primitive, not just our split group. Let's call it increase age. And all we have to do in here is write f at age and increase it with plus equals by 1.0 like this. So every frame, also our age attribute gets one bigger like this. Let's do a quick test in here. Let's maybe visualize our age attribute. And let's maybe do this in here on our solver. And let's maybe work on the visualization because this currently isn't really interesting. Let's set this not to min and max, but to auto. And now if we run this, we see that our very new cells that we just created are this very blue color. And the cells that have been there from the very beginning have this red color. So this seems to be working. What we of course shouldn't forget in here as well is that we also need to convert those attributes as well to points. So for this, let's again go to a prims to points node in here, get two more lines in here, and let's first of all bring in our age, and this should be f at age, and then also the origin, which we called orig, and this should be v at orig. And now to actually animate this, again, we want to do this in a wrangle. So let's make some more room in here and let's use, in this case, a point wrangle, since in here we are on point level now. Let's call it split anim. And what we want to do in here is I first of all want to define a duration for my animation. So let's call it float dur. And this should be equal to a channel float. And let's call the duration as well. Let's create that slider and let's say each animation is 1 second. So let's just set it to 24 frames. And then we can calculate a blend value for our animation from the start to the end. And this is something that we're going to do with a fit. And what we want to put in is our f at h. And this should go between 0 and the duration of our animation. And be remapped or fitted to a range between 0 and 1. And then what this range allows us to do is to finally define v at p to be a lerp between our v at orig and our current final v at p, like this. And the lerp, again, should be driven by a blend value. Let's quickly test this out. Let's see how that looks. And yes, we have some animation. Let's maybe take a look at this in real time. However, the problem that we're having here is that the animation is of course using the sort of equivalent of linear keyframes and is therefore looking quite boring. So we have to implement some sort of animation curves in here as well. And for this, we can, for example, simply use a ramp inside of Houdini. So let's modify our blend attribute and let's run this through a channel ramp. Let's call this anim curve like this. And again, we want to run our blend through it like this. Let's create our ramp. And again, in here, we don't want linear keyframes. We want some sort of curve. So let's create one other handle in here and let's select all of our handles and let's set this to B-spline. And I think this is a much more interesting animation curve in the end. And let's test this. And yes, this is the sort of look that I'm going for here. So we're almost done with this effect right here. The last thing, the very last thing that I want to add is just some animations. And this is where this setup right here is going to differ from the setup that we're going to build in Unreal. Because what we did in Unreal is something that can be done quite easily in Unreal. We built a sort of state machine to get one transition to one state, then wait a bit and get a transition to another state. In Houdini, building the same thing requires just a lot of vex, and I think this tutorial is running long enough. So for this right here in Houdini, I'm going to do the thing that Houdini is just way better at, and that is just running a bit of noise over it and having this drive in the end. One animation. However, if you want to see an implementation of the exact same thing that we did in Unreal and actually write a state machine with this in Vex, please leave a comment. We might do a follow-up video about this if you really want to see that. But let's do the simple implementation here. This is something that I find the easiest to build in VOPs. And also I want to do this before a split anim because a split anim will move our P attribute and we're going to use this P attribute to drive our noises. Let's drop down a point VOP, wire it in between our prims to points and our split anim. And let's maybe call this idle anim. And let's jump inside and let's get building here. So first of all, what we want to have in here is some noise. And for this, I want to use the anti-alias noise. This is just one simple noise inside of Houdini. I want to bring in the position as my noise position as well. But then I also want to animate the offset to again have some sort of animation in here. So for this, first of all, I want to wire in simply the current time into the offset. However, the only thing that I really want to modify about my offset is the Y direction. So let's use first of all a float to vector node, wire the time into the Y component and wire this into the offset. And then I also want to have another offset based on the different point numbers. So what I want to do here is just simply take my PT num and just add it to my time, just to have some variations. So now I have some different animating noise for every point. Next, I want to shape this noise a tiny bit. So for this, I'm first of all going to use a fit range node. And I first of all want to have it between 0 and 1. Minus 0.5 to 0.5 should now be between 0 and 1. And then to just have this look a bit more animated, I want to run this through a ramp as well. And this should be a spline ramp. So let's wire this in here and let's actually set our spline ramp. Let's jump back out. I want to build a fairly drastic curve in here. Let's first of all set both of our points in here. Let's also add some new points in the middle. And let's select all of them and set them to B-spline to have this sort of S-curve in here. And now to make this S-curve a lot more drastic, I want to grab my middle points and just move them very closely together like this. And they're almost touching. And then also bring in the points from the sides. So we have this very drastic S-curve in the middle. And then finally, we want to turn this shaped and animated noise into some attributes. And first of all, what I want to do this, and we can actually get rid of this output node in here, is I want to modify my p-scale attribute based on this. So let's first of all bring this in, bring in our p-scale, and then also export it with a bind export node. And to actually modify it with our noise in here, first of all, I want to run this again through another fit range. And the input will be always between 0 and 1 with a ramp. But in this case, I want the output to be 1 to 0.5. This is the scale range that I want to have in here in the end. And what I want to do with this is I want to simply take this value coming out from here and multiply it with my p-scale. And then pipe this again out as my p-scale. So essentially I'm scaling my p-scale value coming in with a value between 1 and 0.5. This is the first part, and as the second part, I also want to rotate all my pieces. And for this, in the end, I want to export this as an orient attribute. And an orient attribute inside of Houdini is a so-called quaternion, which is a 4-dimensional vector, which sounds really scary, but really isn't, because we have a bunch of really helpful nodes in here. And in this case, I want to use the quaternion node, since we can define or build a quaternion just by specifying an axis and an angle. The axis will be the axis of rotation and the angle will be the angle of rotation. And my axis in this case should be just the y-axis, just the vertical axis. And the angle is something, again, that I want to modify with my ramp. I want to, first of all, multiply the output of my ramp with the angle that I want to rotate, which I'm going to set with a constant. And let's say we want to rotate 90 degrees, like this. So a quarter rotation. And then, since this angle in here expects radians instead of angles, instead of degrees, let's use a degrees to radians node in here to convert this. And then finally pipe this into the angle like this. So this is our final warp in the end. We have our noise section in here and then our animation section in here. And now let's see if that actually works. So let's go back to our output. Let's maybe make this window a bit larger. This is already looking good. And let's see how the animation is looking currently. Oh, and it's looking very, very jittery. And this is because I forgot some settings on my noise. So let's jump back into the attribute WOP. Let's go back to the noise. And the one thing that I want to change in here is I want to turn the roughness down all the way to 0. Let's see if this fixed our issues in here. And yeah, I think those animations now look very MoGraphy. And in the end, we have a nice and procedural grid. So this is it for today. This is how to build a cell grid inside of Houdini. Again, if you want to see one more change to it where we actually build a state machine for our animations in the end, please leave a comment. Let's see how many of you actually want to see this. And until next time, it's cheers and goodbye. And if you like what we're doing, please consider becoming a patron of ours. Not only for supporting Entagma, but also for access to in-depth courses. Like, for example, our Blueprints 101 course that is currently running, which this setup is inspired by. Or, of course, some other courses about getting started with Houdini, how to get really in-depth with machine learning for character animation, and tons of other stuff that we have in here. And also, let me say thank you so much to all our existing patrons. Without you, this channel would not be possible. Thank you.